Okay, welcome to the video for 3.5 equation solving, and we're not going to cover modeling in here actually, just equation solving. I'll have to go back and change that at some point. So our objective is I will be able to apply the properties of logarithms to solve exponential and logarithmic equations algebraically. So first I need you to write down this one-to-one property. And we've been kind of using this before, but I do want you to understand what the property is called. So this is just saying that if you have the same base here, so make sure you write this down. I have the same base and different exponents. Well, because this function is one-to-one, then that means that u has to equal v. Same works for the log. Same base, whatever we're taking the log of, if the base is the same, then they have to be equal. So let's go ahead and use that down here, the one-to-one property for this first problem. Now on all these problems, you're going to want to, let's put a little note here, you're going to isolate the exponential part. Where was I? All right, here we go. Okay, so coming over here, the part that I want to isolate is, that I want to get by itself, is this. Okay, from there we can solve, but first we need to divide by 20 to isolate it. So I would have 1/2 x to the power of 3 equals 5 over 20. I'm going to go ahead and simplify it in this step. So that's the same as 1 over 4. And now my trick here is to get the bases the same. So we isolate, get same bases, which we've done a little bit of this before. So now if I look at this, I can change 1/4 to have a base of 1/2. That would just be 1/2 squared. Once I've done that, now I can use the one-to-one property. So one-to-one property. So that means that the exponents have to be equal to each other, and then I just solve. So I'm going to multiply by 3 on both sides, and I get x equals 6. Okay, so pretty straightforward. There's going to be times, though, that the one-to-one property is not going to work for us. So we have two different ways of doing the same problem. We've already kind of seen this when we learned the change of base formula. But if I subtract 5, because I need to isolate first, then I have 1.05x equals 2. So my first step here is to isolate. Now, in this case, I'm going to rewrite in logarithmic form. So that means I have log base 1.05 of 2 equals x. So rewrite, let's put that in our steps here. And then lastly, well, how am I going to solve this? I'm going to have to use a change of base formula. So I'm going to end up with log base 10 of 2 and log base 10 of 1.05, and then I'm going to grab my calculator and find out what that is. And I'm getting the approximate answer, so I'll do my little squigglies here, 14.207. Okay, so another way, which is kind of the same way as this one, we go ahead and isolate. So we have 1.05x equals 2. But now we're going to take the log of both sides. So I would do log 1.05 to the power of x equals log 2. I'm going to use the property of exponents, or a property of logs, to pull that x out. And now these are just being multiplied together. So I can divide x equals log 2 over. And now you can see I have the same thing as I had going on over here. So when I go to plug this in the calculator, I am going to get the same answer. X is approximately 14.207. So these two ways are just to reinforce how these things relate and just to have a deeper understanding of logarithms. All right, let's move on. So that was solving an exponential function. Now we're going to solve a logarithmic function. Okay, method 1, one-to-one properties. So again, in this case, I don't have to isolate. You will have situations where you do have to isolate. So if I were to have, let's say, this on here, right? I would actually have to subtract the 3 in order to solve this problem, but that's not what's going on here. So let's just go ahead and get to the one-to-one property. And the way to do that is you need to get that same base, right? So we always isolate first. So let's put that in here. Isolate log part first. But then after that, we want to get same base. So let's think about how to do that. Well, this is just base 10, right? So we have already log base 10 x squared equals, well, we want, again, a log base 10. Well, what can we do here to make sure that this is the same as 2? Well, remember that if you have log 10 of 10 with an exponent, all of that would just simplify down to 2. So that's what we're going to do. So now I have these matching parts here. I have log base 10 and I have log base 10, and that means I can just put the x squared equals 10 squared. Simplify this, x squared equals 100. Find the square root, and I get x equals, now I'm going to get 2 answers here, right? I'm going to have the positive 10 and negative 10. All right, another way to do this. Rewrite in exponential form. So that would be, this is a log base 10, so we would have 10 squared equals x squared. So we're rewriting, and then we're going to use the, oh, sorry, we're not using the one-to-one property here. In this case, we just rewrote it, and we can just go 100 equals x squared, take the square root, and we end up with, again, x equals positive or negative 10. Okay, I need to show you one more thing here, something you have to be careful of. Here, if we wanted to use the property of logs, it does not work out the way we would expect it to. So if we were to go 2 log x equals 2, right? These are being multiplied together, so I'm going to divide by 2, and I have log x equals 1. Then I rewrite, and I have, because this is a base of 10, I have 10 to the power of 1 equals x. Well, this is incorrect. We've lost one of our answers here, right? So 10 to the power of 1, we just have x equals 10. We're missing an answer, so very important. Okay, so let's see why this is really quick. And you don't have to write this down, but just so you understand, the graph of log x is different than the graph of log x squared. Remember, in log x, no negatives. Remember, in here, because we're going to square this, it's okay to have a negative in there, right? Negative okay, because you're going to square it and it's going to become a positive. This graph looks like this, whereas this graph looks like this. Right, so we're seeing that we have, that's a poorly drawn graph, but we're seeing that we have answers for negative x's, right? So what happens here is you're just deleting one of the answers when you do this, so you have to be careful. Now, up here I said, go ahead and use this property and bring it down, but it was a special exponent. We have an x. So it's okay to bring it down when you have an x, but notice that when you have a squared, that messes things up, and that would be true for all even exponents, actually. All right, so we have another way to solve logarithms. Sometimes we're going to have to condense first, right? So in this case, instead of isolating, we actually have to just go ahead and condense this down all to one logarithm in order to solve it. So our property says that if we're adding 2 logarithms, we can just say that this is the log of x times x plus 21. So now let's go ahead and rewrite this in exponential form. So we have 10 squared equals x times x plus 21. Looks like we're going to get a quadratic here. This is 100 equals x squared plus 21x. So now 0 equals x squared plus 21x minus 100. I'm going to try to factor this, see if it is factorable. X, I'm thinking, okay, 25 times 4 Looks like it's going to work out for me. And now I need the 4 to be negative, the 25 to be positive. These do, in fact, would add back up to 21, and they multiply to negative 100. Okay, so it looks like I have a couple of answers here. It looks like I have an answer of negative 25 and negative 4. But remember, we can't have any negatives up here. You cannot have a negative inside the log. That doesn't necessarily mean that negative answers are incorrect, right? Negative x says, oh, sorry, that's actually a positive. It's not always going to mean that because you got a negative answer here, that it's extraneous. You're just going to have to plug them back in and find out. So if I were to plug the 4 back in, does that cause any negatives? Well, 4 plus 21 is a positive, and 4 here, that's a positive. So this answer checks out. But negative 25, if I do negative 25 plus 21, that's going to give me a negative 4. So my negative 25 is not actually an answer. This is an extraneous solution here. So we'll get rid of that, and that means that x equals 4 is the only answer that's going to work here.